Hi, welcome to Mat210. What we're going to do today is discuss higher order derivatives in calculus. But before we start in on that, I want to go over a couple of things that I noticed on the last quiz on 1.6. Some it wasn't exactly mistakes, but it wasn't that you were doing the problem completely. You weren't quite completely finishing the problem. Let's take a look at the very first problem. Y equals 3 square root of x, I believe it was, times x cubed, right? Now, normally what we would do is just multiply these together. And I'll do that in a second, but they wanted to kind of use that rule I was showing, the AB prime, ABBA, AB prime plus BA prime. So that's okay. Yeah, they wanted you to do it that way. There's an easier way, but let's try that and see. So the first thing we want to do is break this out of the square root. This would be 3x to the 1/2 times x cubed. Okay, so we're going to find our first derivative. First derivative is equal to a, which we're not doing anything to, times the derivative of b, which would be 3x squared, plus b times the derivative of a, which is 3/2 x to the negative 1/2. Huh? Okay, so that's basically what you did, but it's not finished. I mean, there's a lot of terms here, and we don't want this plus sign there and all these terms. We want to combine those terms together, and this is where we're going to use our algebra. So the first thing we're going to do is, of course, simplify this first term. Let's see, we could factor something common out, like an x squared and some other things, but I think on this particular problem, it'd be easier just to simplify this. So 3 times 3 is 9, and when the bases are the same on our x, when the bases are the same, we're going to add the powers. So that would be x to the 2.5. But you're not going to write 2.5 down like that. You're going to write 5/2. Plus, now you're going to do the same thing here. 3/2 x to the 3 minus, again, your bases are the same, so we're multiplying them. This is a multiplication problem. So we're going to add the exponents, which again comes up to 2.5 or 5/2. You see, so they both have 5/2. So now both of these are like terms. And we have 9 plus 3/2, or we could say this is 9x to the 5/2 plus 1.5. You could do it that way, I guess. X to the 5/2 is 10.5 x to the 5/2, or 10.5 or something like that. You want to bring it down as far as you can go, Now, the easier way, after we simplify this, would have been just to multiply these together, okay? So if we were going to multiply these together, this would be, this is still y, this would be 3. We would add the exponents, 2.5 or 5/2. Okay, so now we could take the derivative. 5/2 times 3 would be 15/2. Is that right? Oh, wait, 3 plus 1/2 would be 3.5 or 7/2. Excuse me. And then 7/2 times 3 would be 21/2. Writing it backwards. X to the, subtract 2 2's, 5/2, which is the same thing we had. You see, and of course, this would have been faster, but they wanted you to get to practice with using this rule here. So when you do that, you can't just stop and say, I'm done right there, because you're not done. You have to do a lot more work to it. Let's look at the second problem. The same thing kind of happened on the second problem. See there? You had y equals parentheses square root of x plus 1 times the square root of x plus 2. And of course, it would have been easier just to do a FOIL and then take the derivative. But again, they wanted you to get practice with the ABBA. And this was AB prime plus BA prime. This was with the same thing with the product rule and all those. They want you to simplify it. They don't want you to just stop. So let's rewrite this: x to the 1/2 plus 1, x to the 1/2 plus 2. All right. So you went ahead and what you did was good. You started doing the ABBA, x to the 1/2 plus 1 times the derivative of b, which is 1/2 x to the minus 1 would be negative 1/2, right? Plus the derivative of 2 is 0. Okay? Plus the second, x to the 1/2 plus 2 times the derivative of the first, which comes out to be the same, 1/2 x to the negative 1/2. And then you stopped. You don't want to stop right there. Look at this problem. They both have this common factor to both the terms. Plus, we're trying to put it all together into a nice little compact equation like we did the first one. We don't want it all spread out like this. So we're going to factor this out. This would be 1/2 x to the negative 1/2. We're going to factor that out times x to the 1/2 plus 1 plus x to the 1/2 plus 2. See, we want to go this extra step. Now we can kind of combine this together. Y prime equals 1/2 x to the negative 1/2. And we can rewrite that a little bit later. Here you have x to the 1/2 and x to the 1/2. Those are like terms. It's not going to be x to the 1. It's going to be 1 plus 1 is 2x to the 1/2. See, this is where the algebra comes in, plus 3. Now what you could do is you can bring this x to the 1/2 down. So let's rewrite this in a little bit nicer form. This would be, you could put your 1 up there if you want, but basically on the bottom you're going to have 2. You're going to bring this down, and that would become the square root of x. And then inside the parentheses you have 2 square root of x plus 3. You could leave it like that. Pretty good answer, but you notice there's something here. You don't want to cancel that yet. We've got the sum over a total here, so we can put each part over 2 radical x, and we can put the 3 over the 2 radical x. So this would cancel out and give us 1, not completely canceled out, plus 3 over 2 radical x. So this would also be a solution to this problem. I guess you could leave this also, but oops, I'm sorry, I wasn't showing it, but I put each part over that. So you could leave it in this form, or you could put it in maybe a simpler form. Either answer would be acceptable, but you see, this is not really acceptable. This is like you haven't really completed the problem. You got a good start on it, and what you did was correct, but it's a start. It's not the finish. It's like working on an engine and it doesn't turn over in the car. You know, you put in the engine, but it's still, the car isn't running. You got to hook up the carburetor and the linkage and all that junk. So the same thing happens here. You haven't quite finished. You got a long ways to get to the answer. You're not there. You're partially there. So you want to be careful when you're doing these things to make sure that especially like you're going to be using the chain rule. You want to make sure just because you use the chain rule and you have a long expression, you're not done by a long shot. You have much more work to do. Your work is to get it down to an expression, and usually we like an expression that's something over something. So this is probably a very good expression right there. Just something very simple, not something all strung out. All right, so you've been reprimanded. And now we're going to look at higher order derivatives. Okay? So this is 1.8. And one thing about higher order derivatives is they're not quite as hard as what you've been doing. They can get difficult. We can always take a math problem and make it impossible, you know. But what we're going to do is just try to make it as basic as we can. So let's start out with a problem here. This is the one in the book. Okay, so they could call this y. They could also call this dy over dx. They could also call this function of x. They could use a capital F or a small f, doesn't matter. We got different forms that we could put it in. Y equals dy over dx equals the derivative of y with respect to x, function of x equals. So there's a lot of different ways we can write this. When we take the first derivative, that's why we put a little 1 there, because that's the first derivative, or we call this y prime. This would be 5x to the fourth, right? Minus 12x to the third plus 1. Okay, no problem. We could have also written that as, this would, as, well, it would have been written as dy over dx. I should have kind of jumped the gun, or function prime x. Now, let's take the next derivative of this. This is what we mean by higher order derivatives. We take the derivative of the derivative. So we're going to signify this with a little 2 there. And that would be 20x to the third. We take the derivative of the derivative minus 36x squared plus 0. Okay. We could signify it this way also. We could say now we're taking the second derivative of y over dx squared. This is a little fancier. This is Leibniz notation. You know, we can use this notation, but, and we will on certain problems. We don't use it that often. If we use this notation, we usually put a double bar x like that. So we can signify second derivative this way, or this way. You know, this is a little bit more formal. Let's take the third derivative. So we could put a little 3 up here. Sometimes they do that, or they just put a 3. You know, if you keep getting higher and higher, then you probably want to put some number. This would be 60x squared minus 72x. And again, we would show this in Leibniz notation. This would be the third derivative with respect to the third derivative of x. So those two numbers would match up. And then we could also write it as f. If we're going to put use a number here, we usually put it in the parentheses. Like we could write it like that. We're taking the third derivative. Okay, let's take the fourth derivative. We can use IV, or we could put a little 4 here. That would be 120x minus 72. And again, this would be d to the fourth y over dx4. Or we could write it as this notation. So there's a lot of different ways we could write this. Okay, so you know, sometimes they use function of x, sometimes they use y. Usually we use the y because it's faster to write, you know, but can we take another derivative? Yeah, let's go ahead and take the fifth derivative. What would that be? That would be 120. And then finally, the sixth derivative is 0. So sometimes they're worked on as zeros, but it depends. if you have negative exponents, this problem may never end. You could just take the derivatives until you're going crazy, you know. So again, if I took the sixth derivative here, it would be, Leibniz notation would be d6y over dx6. Now, a little fancier. And if I did it here, I'd probably put function of 6x. And I guess you could use a Roman numeral, like you could use, what is 6xi, you know. Usually, not xi, what is a vi? But we usually don't, you know. By the time we get up to 4, we just want to write the number down. So different ways to do it. So that's what we mean by higher order derivatives. We take the derivative of the derivative. So we do want to simplify the problem a little bit, but sometimes you don't want to simplify it so much that it gets difficult to take the next derivative. All right, so let's try a couple in the book. Here's one. Here's an interesting one. It says, for y equals 1 over x, find, using Leibniz notation, the second derivative. That's what that's saying. Find the second derivative. So we could write this as, first of all, let's bring this up to the top. We don't want it written this way, so let's write this as x to the negative 1. So the first derivative, using Leibniz notation, would be this symbol. And what would that be? That would be negative 1 x to the negative 1 minus 1 would be negative 2. And again, if we were just going to take the first derivative, then we would simplify that and write that as negative 1 over x squared. See, we would put it in a better form. But because we're going to take additional derivatives, you don't want to simplify it yet. Okay, we're going to take the second derivative, unless it was like a real long expression that you could simplify. But if it's something simple like this, we don't want to. So we're going to take the second derivative. And you want to get in the habit of writing this down so people know what you're doing. They know you're taking the second derivative. So this is 2 multiplying x to the negative 3. Now, if that's as far as we're going to go, then we would simplify to 2 and bring this down, x cubed, 2 over x cubed. But you wouldn't simplify it this step like I did over here, because then it's harder to take the next derivative if it's in this form. We're going to have to move this back up, and, you know, you're kind of self-defeating yourself. But when you get to the last step, you definitely want to simplify. All right, let's try another one in the book. Look at this one. Y equals x squared plus 10x to the 20th power. They want you to find y prime and the first derivative and the second derivative. So they want us to do both. Okay. Well, let's go ahead and is this 20 on the outside or the inside? It's on the outside, so that makes a big difference. We want to make sure that's on the outside. So right here, when I see a parentheses and I see a power on the outside, bingo, chain rule. This is the chain rule problem. So y prime is equal to 20 times the parentheses to the 19th power. That gets rid of the 20. Now that's the outside. Now we got to take the derivative of the inside. Derivative of the first term is 2x plus the derivative of this term is 10. Now, obviously, we can't made a mistake. Let me go back. I'm sorry about that. Y prime, why don't we do this again? This would be 20 parentheses 19, but this stuff stays, x squared plus 10x, my mistake. Now we're going to take the derivative of the inside, 2x plus 10. There we go. So it's the derivative of the outside, but we keep the parentheses. We don't change it. Then we take the derivative of the inside, the parentheses. So my mistake. Now, what they did here on their next step is they tried to simplify it a little bit. Because of this 20 out here, you're still going to have to, even when you simplify it, you're still going to have to do an ABBA on it. You could leave it the way it is and then do the ABBA. We do it to see if maybe it was easier to do what they did. They went ahead and they saw that this could be factored. Not this one. You can't factor when you're raised to a power. You cannot factor this out into to do the power, but this has a power of 1, so you can do that. And you can take the 2 out. If you could take an x out, you would try to do that too. And then they multiplied the 2 times the 20 and got a 40. I don't know, this might be easier, might not be easier, I don't know. So that's how they got it down to this step. That's what they did, and we're kind of right it that way. That's the way the book did it. Okay, now we're going to go hunting for the second derivative. Now, we're going to consider this all one term right here. We're going to consider that one term. That's your A, and this is your B. So we have to do an ABBA on it. So this is A. Does it have an X in it? Yeah. To the 19 times the derivative of B. B would be just 1, huh? Now, you wouldn't have to write that down, but I usually do because I want to, and the book did also, because we want to kind of show that we did take that derivative. Plus, and I know I'm going to run out of room here, plus B times the derivative of A. Well, the derivative of A is going to be 19 times 40. If you want to do that right away, I guess you could. Real handy here. 19 times 40. I think it's 760, but let's double check it. This is a lousy calculator. Okay, but it did come out to 760. So it was, let me get my bearings straight. B times the derivative of A. So that was 760 x squared plus 10x to the 18th power. And now we're going to take the derivative of the inside, which is 2x plus 10. Woo, what a mess. Okay. Well, but just 2x plus 10. Yeah, want to make sure I didn't make a mistake. So here's where your factoring skills come in. You're going to take out this x squared, but or did they factor it at this point? Let's see. They went ahead and factored out this parentheses right here. And I can see why, because there's kind of a matchup with this. So let's try that. They didn't do anything to the first one. Okay, you can't factor out an x because it's to the 19th power. But you can factor this out, and I'm going to write it here so I save a little bit of space. I'm going to take out the 2, and we got x plus 5. So if you notice, we got 2 times 70. We can multiply that out. What would that be? This is going to be plus 2 times 70 would be 0, 12, 15, 20. And then we see that we could take out, we get an x plus 5 and an x plus 5. We're multiplying, so that would be an x plus 5 squared, huh? Got two of these, and they're timesing, just like we can multiply 2 times 70. And then I noticed that they could take an x out of here. Did they go ahead and take that out? Or did we make a mistake? No, we don't want to take that out. Okay, let's leave that. We can't take it out because it's to the power 18th power too. I couldn't take it out if I wanted to. Okay, so that's what I have. Now, what I noticed is this is common to both terms, and 40 will go into both terms. So we're going to divide everything by 40. I'm going to write that down as our common factor. And then we're going to divide everything by x squared. Whoops, there. Let's put it down here. X squared plus 10x to the 18th power. X squared plus 10x to the 18th power. And that's what we're factoring out. So what does that leave me here? Well, that just leaves me with, let's put a bracket here. That leaves me with x squared plus 10x to the 1 power. So I don't need to put the parentheses. Then here I'm going to divide 1520. I think it'll divide by 40. 1520 divided by 40, 38. Okay. 38. X plus 5 squared. And that's what I get when I factor out the 40 and I multiply I take out the x squared plus 10x to the 18th. Now what I want to do is simplify this some more. I want to figure out what's all inside this bracket. We're not quite done yet. So this would be x squared plus 10x plus 38 times, and I'm going to do a square double square here, x squared, multiply these together and double, and then square. In other words, I'm going to do a FOIL on that and expand it out. Then I'm going to distribute that out. So I'm multiplying the 38 times the x squared plus 380x plus 38 times 25, 950. What a mess, huh? All right, I still have this in front. So I'm going to get another sheet of paper because I ran out of room here. I'm going to put this down. So you can see these are just a ton of fun. So y2 is now 40 times x squared plus 10x to the 18th. And now I'm going to simplify this whole thing. Okay, I got an x squared here, I got an x squared here. I've got a 39x squared. I've got a 10x and a 30x, 380x, I should say, is 390x plus the 950. Now, it might be possible that you could divide all these by 3, but see, 3 won't go into 950. If you add up the digits, 9 and 5 is 14. It would have to be a 15. So we can't divide these by 3, so good chance that this won't factor out. You know, if you could factor it, then you would have factored it down, and you could do some of that stuff, or you could take a common factor out of it. But this won't factor. But you notice it's like something times something times something. They didn't leave it right here where it was something plus something times something, you know, kind of a thing. So this is a little trick I use when I want to take out a common factor. This 40, I put it under each one so I can actually see my cancellations. I can see that this gave me the 18, you know, and I did the same thing. Was it to the 1 power? It wasn't to the 18th power, was it? Yeah, it was to the 18th power. Okay. So you want to kind of make sure that you kind of show those kinds of things. Yeah, I think I got it. Anyhow, so you want to work through, you can see, look at your book. It's not finished until it's some of these things. Okay, so that's basically what the second derivative is. They're not always that hard, but some of them get kind of interesting, And look at your, try some out of the practice set and then see what their answers look like compared to your answers. If your answers don't match up, that means you probably didn't simplify it enough. It probably you're on the right track, but you're not quite there. So I hope this helps. We could try one more. See if there's one in the exercise. I could do a very easy one. Let's try this number 13. See if we can. This one isn't so great. I'm trying to see one that's harder. Let's try 25. Well, this one's not too hard either, but we'll take a look at it. So this is really in a pretty good form to start off with. I want to take the first derivative. So this is just 2/3 x minus 3/3 would be a negative 1/3 plus 1 times 4 is 4, x to the 0. Okay, so not too much we can do to this, I think. Let's see what they did. Well, let's write it this way. Oh, they wanted the second derivative. Oh, I was going to say, that doesn't look like the second derivative. Okay, they wanted the second derivative. I'm sorry. So we want to multiply 1. See, I don't want to simplify that yet. So negative 1/3 times 2 is negative 2/9. X minus 1 would be a negative 4/3. And this would be 0. Now, at this point, you could probably leave it that way. We usually don't like a negative exponent, but you could leave this in exponential form. You could leave it as 4/3, but you just want to put that on the bottom there. We don't have to worry too much. Let me double check the answer. We don't have to worry too much about, they don't usually rationalize too much in the book. I mean, sometimes they do and sometimes they don't. It's inconsistent. But yeah, make sure you read the directions. We wanted the second derivative of this function. So here was the first derivative, but I didn't simplify it. I could have written it like this. 2/3 square root, cube root of x plus 4, But then once I got it in that form, then it would be hard to go back to this. So it's better if you're going to take the second derivative. You have to do some simplifying sometimes, but not tremendous amount. But when you get to the final answer, see, like on this one, we didn't do too much simplifying until we got to this point, and then you didn't want to leave it like that. There's a lot of work to do, especially this part when you had to do the ABBA on it. It gets pretty messy, and especially when you have, here you had ABBA with chain rule. So that is always a challenge. So hope you enjoyed.